Okay, so there's a lot of stuff that you guys wanted me to go over, and so I'm going to try to do the best I can in the limited time that I have for this video. So here we go. So we're going to start off with thermal expansion. Okay, thermal expansion. So this is the L changes a lot. So we got alpha, LO, delta T. Okay, so this is talking about how if you heat something up, that object will expand, the material itself will expand because the molecules are moving faster, things like that. So just a quick example, here we go. We have a rod. That rod is made out of steel, okay? And we have to look up, or we have to be given the alpha. Remember, the alpha is known as the coefficient of thermal expansion, and for steel, that is 12 times 10 to the negative 6. It's got a unit of inverse Kelvin. Okay, we're going to say this metal rod is 2.5 meters long, and the cross-sectional area for it is, oh, you don't need it. You just need 2.5 meters long. All right. You also need the temperature. So we're going to heat this up from 20 degrees Celsius to 50 degrees Celsius. Okay, that's where we're going with it. So here we go. If we're going to calculate this, its L changes a lot, so delta L is equal to the alpha of 12 times 10 to the negative 6 inverse Kelvin, multiplied by the original length, 2.5 meters, multiplied by the change in temperature. And if we're going from 20 degrees Celsius to 50 degrees Celsius, then not 50, it's going to be 30, right? That is the change. Okay? So degrees Celsius, because it's a change in temperature, will cancel out with that Kelvin there. We just have to multiply everything together, and change in L is equal to 9 times 10 to the negative 4th meters if you stick that in your calculator. Okay, so I would suggest you do it. Check me on it. All right, now if we're talking about area expansion, if we got something that's got a hole in it, and the whole thing starts to expand, okay, so it expands outward. This expands, all the dimensions expand. What happens to that hole? Does the hole close up, or does it enlarge? So this is like a picture enlarging. The hole itself will also enlarge as well. Okay, so it's not like everything goes towards the center. And remember, we had the argument that what if the hole wasn't there? If you were to heat this metal sheet up and then punch a hole in it, that would be the same thing as punching a hole in it and then heating it up. So you would have that same size there, or a bigger size whenever it heats up. Okay, so the thing is here is that the hole expands along with the rest of everything else. Okay, so that's thermal expansion. There's volume expansion too, but really they won't be asking about volume. It'll just be linear expansion and area expansion. All right, so the next thing we're going to talk about is heat current. Okay, heat current. So this is saying that with your you have an object. Let's say here it is, and it's got some extent to it. Okay, let's try that again. Okay, it's got some thickness to it. So here's a thickness or a length of it. Okay, it has a change in temperature or a difference in temperature from one side to another. So let's say the back side of it is some temperature Tc, and the front side of it is some temperature Th. Then we know that heat is going to flow spontaneously from the hot to the cold, and it takes some amount of time for that to get there. Remember heating up the rod in class, and we had the thermometers on it, so it took some time to get to the certain locations. So if we want to calculate that, there is a given equation for it, and that equation is Q over T, the heat or the energy per unit time, which is a watt, it's power, is the equation Ka, that's not an A, okay, Ka delta T over L. Okay, where K is a coefficient. It's not known as a coefficient. It's known as the thermal conductivity. Okay, it is a coefficient. It's just not called a coefficient. Thermal conductivity. Okay, thermal conductivity. Okay, if I'm going fast, you can always slow me down, listen to me a couple of times, pause me, whatever you need to do. So let's do an example here. We got the same steel rod. Okay, now we're talking about thermal conductivity and not expansion. So the K for steel is equal to 16.7 watts per meter Kelvin. Okay, 16.7 watts per meter Kelvin. If we have a 50 degrees Celsius over here, and we have 125 degrees Celsius over here, and there's where I need our cross-sectional area A, that is going to be 0.25 meters squared. So that gives Q over T is equal to 16.7, with that weird funky unit up there, multiplied by 0.25 meters squared, multiplied by 75 degrees Celsius. Okay, and again, this Celsius will cancel out with the Kelvin. That's in that unit, and divided by the length of 1.5 meters. Okay, it doesn't have to be a cylindrical rod. It could be a square rod or square glass pane or something like that, like it is here. And if you were to calculate all that out, you would find it's 209 roughly joules per second. Okay. Now I suggest you take a look at joules per second and see how that unit turns into it. Now you're really looking at just a watt, right? A watt is a joule per second. So how do you get that watt? What cancels out to get that? All right. Next topic. Heat engines. So we have an engine here. Okay. We have a hot reservoir up here. Hot. There we go. We have a cold reservoir down here. There we go. And we know that heat will spontaneously flow QH down here, QC, and that engine is doing something along with that. So QH will flow from hot to cold, and that engine is taking some of that energy and trying to do a little bit of work with it. So we know that QH is the available amount of energy. We do some work to it. We dump some of that energy out. So conservation of energy says that equation will apply. Okay. We know that efficiency is equal to the work divided by the QH. It's basically saying how much did we use out of how much was available to us. Okay. Another way of looking at efficiency is if we were to solve this for work, it would be work is equal to QH minus QC. And if we were to plug that in right there, we would get that that equation turns into 1 minus QC over QH. Okay. Now, if we're talking about an ideal engine, that's a Carnot engine, right? A Carnot, C-R-O-N-O-T, that's an N right there. Okay. And the Carnot efficiency, that's an ideal engine, is 1 minus TC over TH. So we're dealing with temperatures, instead of looking at the actual energies. But that's ideal. So let's do a quick example for that real quick. What if we have temperatures where this is operating between 2400 degrees Kelvin and down here in the cold it's at 500 degrees Kelvin? Okay, what is the efficiency of that engine? And this would be considered maximum efficiency. It's the biggest that we can get. So that's 1 minus 500 over 2400. And you would see that that is about 0.79 or 79%, which would be a really, really good engine, better than anything that we've been able to build anywhere in the world. Okay, so that's efficiency. You would do the exact same thing if you were given information about the actual joules of energy that were given from one place to another, but with a Carnot cycle, we can look at just the temperatures instead of just the energy. All right. Let's review PV diagrams real quick. Okay, so PV diagrams. If we have an let's start with isochoric. Okay, isochoric. PV diagram, that's a same volume. It's just going to be an up and down line. Okay, whether it's going up or whether it's going down, we don't know. It depends on the process, whether you're increasing pressure or decreasing pressure. So here, work is equal to 0. That means your internal energy, whatever you do with the internal energy, has to come from heat. So if you give heat, you increase internal energy. If you take away heat, then you decrease internal energy. And that would be whether you go up or up or down this process. That's going to be whether you're giving or taking away heat. Okay. Next one. Isobaric. Isobaric, right? PV diagram. What does that look like? Isobaric, same pressure, it's just straight across. Now, whether it's going right or going to left, that's going to be whether you're increasing volume or decreasing volume, right? In this case, we know that work is equal to a negative pressure change in volume. Remember that negative. That negative has to be there, because if your volume increases, that means the gas is doing work. Okay, the gas is pushing the cylinder back out. If the gas is doing work, that is defined as being negative. Okay, that's a negative work if it's being done by the system. Positive work if it's being done on the system. Okay, let's keep going. So isothermal. Isothermal. Isothermal is a PV diagram that's a little curved. Okay, isothermal. There we go. There's an isothermal line. That means delta U is equal to 0. If your temperature is not changing, then your kinetic energy of your particles are not changing. And therefore, the internal energy is not changing. You're not increasing kinetic, you're not decreasing kinetic. You are simply staying the same temperature. Let me make that a better U. There we go. Okay? So that means any Q that you give is going to be negative work, or vice versa, that work is equal to negative Q. So if you input heat, you have to do work with it in order to keep the internal energy. So if you input 5,100 joules of heat, then you have to take out 51 joules of that same energy in the form of work. It has to do 51,000 joules of energy, 100, whatever I said, of energy, of work, in order to account for that. Last one, adiabatic. Okay, pressure versus volume diagram. Looks a lot like an isothermal line, except that it is much more steep. Okay, much more steep. That's going from one isothermal line to another isothermal line. Okay, so you have to remember that. If you have two curved lines and one's steeper than the other, the steeper one is the adiabatic one. So delta Q, or not delta Q, but just Q. You're not losing or gaining any heat. Q is equal to 0. So any delta U that you have is going to equal the work that's done. Okay, if the gas does work, that means it gets colder. All right, if it does work, whether it's going an increasing volume, it has to get colder because you're taking that energy away from the internal energy. If you do work on it, that means you're going the other way along this line, and that's going to increase the internal energy. You're compressing the gas. You're increasing the temperature. All right. I would love to work a full-blown problem for you, but I'm going to be running out of time. So if I just show you this PV diagram, okay, we're going to go from A, which is right here, up to B, right here, over to C, right here, and then C back to A. So C to A is not one of our processes that we've been talking about, okay, but we can know a few things about the C to A process from looking at A to B. All right? So from A to B, in order to stay at the same volume, you are not doing any work whatsoever, okay? But in order to increase your pressure, you have to input heat. You have to input heat, increasing pressure, increasing temperature, so you're increasing that internal energy, okay? From B to C, you are doing some work, okay? Who's doing work? Are you doing work, or is the gas doing work? From B to C, the gas is doing work, and what I'm doing is going A, B, C, so we're going along this way. So B to C, the gas is doing work, okay? So that is work that's coming out, negative work coming out, all right, from B to C, okay? You could have Q coming in. You could have Q coming in, okay? You might not. You might not have Q coming in. If no Q is coming in, no Q is coming out, then that work is affecting the internal energy. Okay, so more than likely you will have Q coming in. All right, so we've increased internal energy from A to B. We've increased internal energy maybe from B to C. So C is the highest internal energy state. Okay, it is the highest temperature. You're in the highest pressure, largest volume. In order to get back to A, you have to dump all that energy because we know delta U has to end up always being 0. So whatever heat came in here, whatever heat came in here, whatever work came out here, we have to do some work, and I know we're doing work. Work is coming back into it because we're decreasing volume, but we have to take Q out in order to get yourself back to a delta U of 0. Okay. If you have any questions, ask me at the beginning of class. Watch this a couple times if you need to. See you tomorrow.